Okay, so polygons, polygons, polygons. Let's see. We can solve real-world problems with angles, and that relates more to our SOL, but we're going to just talk about them in general. This should be a good bit of review. So what is a polygon? A simple closed figure formed by three or more coplanar line segments, sides meet at endpoints called vertices. So what does that mean? Simple closed figure. What closed? What does that mean? What does that mean?
That it's not just one line.
Yeah, it's not like this. Is that closed? It's a smile, but it's not closed. So closed is like it goes in on itself. Formed by three or more coplanar, so they're lying in the same planes. It's a two-dimensional shape. Line segments, we call those sides. So they're segments, little lines together. And they meet at these endpoints. We call these endpoints vertices. One of them is called a vertex. So how can we tell if something's a polygon or not? Do they meet the definition? So if you're looking at this shape here, and your directions are to do what? Nothing yet. Circle or put a square around, I think. First of all, is this a polygon?
Yes.
Why is this a polygon? Is it a simple closed figure?
Yes.
Does it form by three or more coplanar line segments?
Yes.
And do the sides meet at endpoints? So that one is one. Is this a polygon?
No.
No. How come? Not close. Polygon?
Yes.
Polygon?
No.
Well, it's a closed figure. What's the problem? Not line segments. So no. Polygon? Polygon.
Yes.
Okay. Wow, great. We know what they are. So concave versus convex. So there's two different kinds of polygons. If it's concave, it contains a reflex angle. And a reflex angle, if we remember our angles, we have acute angles that are less than between 0 and 90. We have right angles that are 90. We have obtuse angles between 90 and 180. And then we have reflexes, which are bigger than 180. And then convex polygons do not have reflex angles. So what do we mean by that? A concave angle, I like to think about it caves in. That helps me remember which one is concave. So for example, this one is called a convex polygon. None of these are reflex angles. Look at these angles. They look about at least less than 90. You can have an obtuse one in there, but they're not reflex. So this is convex. So we're supposed to circle or put a box around convex. Now this guy here is going to be concave. Because this angle here, look at that, it's bigger than 180 degrees. That's a reflex angle. And it kind of caves in. I'm going to circle that guy, right? So is this one concave or convex?
Convex.
Convex, it does not have, it doesn't cave in anywhere, right? These angles look like probably only triangles, but maybe not. So we're gonna, we put a box around those. And then what about this guy?
Convex.
Concave. Now look at this angle here, right? So this one is your concave. So if it has an angle in there that's bigger than 180 degrees, that is a concave polygon. Make sense? Kind of. What else we got here? A regular polygon. A regular polygon, by definition, that means it's equilateral and equiangular. We've already worked with one kind of regular polygon, which is what? Square is, yeah, a triangle. We've done a lot of work with equilateral triangles, right? Equilateral, equiangular. So any polygon is regular if it's equiangular and equilateral. A new word we have to know, vocabulary here, diagonal. And I think you kind of know what a diagonal is. Let's look at the more formal definition. It's a line segment in a polygon here that connects two non-consecutive vertices. And what does that even mean? Non-consecutive, yep. Yeah, they're not next to each other. Consecutive, one right after the other. Non-consecutive, not. So these two vertices are consecutive. This is not a diagonal. So if I skip one and I go from here to here, that's a diagonal. I'm skipping, right? I'm skipping around these to get from here to here. They are not consecutive B and A. The B and A are, so that's not a diagonal. Okay, so non-consecutive vertices, we call those diagonals. Excellent. How do you name them? And that was our warm-up to kind of like remind us how we do that. So what do we call three-sided polygon? Let's go ahead. That's right. Right. What do we call a four-sided polygon? Yeah? Quadrilateral. You might have been thinking square or rectangle. Anybody think about that? Those are kinds of quadrilaterals. But the overall name is quadrilateral, four sides. This one is three angles, five sides. Yes. Yes, we're Washington, D.C. based. You know this. Like the rest of the country, it doesn't come so easy. But Pentagon, five sides. And we have that building in Virginia. Six sides. Yeah? Hexagon. I mean, hex sounds a little like six. It's hard to remember. Seven sides. Mason. Heptagon. 8 sides. Yes, sir. Octagon. Octagon. I think that's how you spell it. Just looking at it. Okay. 9 sides. 9 sides. Yes, Andrew. Nonagon. 10 sides. Yeah, Tejas. Decagon. 12 sides. Brendan. Dodecagon. I think do is kind of meaning 2, and deca is 10. What about n sides? Yeah. Close. Well, let's do that in Greek. We call that an n-gon. So you could call this a 3-gon if you want. You can actually call it a trigon, right? So we're kind of like mixing up these different ways of naming them. But these are the standard naming conventions. If you don't know what to call, say it has like 26 sides. What do you call that? I don't know. You can say it's a 26-gon. That is kind of the shortcut. And I think I found some of the other names that we don't necessarily know. Like, okay, we're good up to 12, 13. Triskaidekagon. 14. Tetrakidecagon. What's this thing? I think this was on the warm-up. A pentadecagon. So you see the 5 and the 10. Hexadecagon. Heptadecagon. What is that? Heptadecagon. Octadecagon. So, what does that say for 20? Icosagon. Okay. You know, all right. So if you're good and you want to remember that, fantastic. Chances are you put that on paper, I'll be like, what is that? So, but you got to know these. These ones we have to know by its fancy name. Anything bigger than 12, I'm okay with this notation. All righty. Theorems. That's why we're here for theorems. What? What was that? What was that noise? Was that? No. It was yay. Okay. Polygon interior angle theorem. This is an awesome little theorem here. This theorem tells us how to find what all these angles add up to. Like in a triangle, what do they all add up to? What do they add up to in a quadrilateral? 360. What about a pentagon? What about a hexagon?
720.
What? You know this? What? What about a 26-gon? Oh, okay, silence. Okay.
720,000.
How's it 3? Why is it? Okay, well, rather than memorize every single possibility, we have a theorem, and this is the theorem. The theorem says if you have an n-gon, and n means the number of sides, right? So if this is a 3-gon, you have a triangle, 5-gon, pentagon. You're going to take that number of sides, subtract 2, multiply by 180, you get the number of degrees in there. So like for 3. Okay, she plugged in the formula? All right, she figured it out now. So think about a triangle. A triangle is a 3-gon. 3 minus 2 is 1. 1 times 180, that's where you get the 180. How about a 4-sided figure? 4 minus 2 is 2, right? Times 180, 360. So we can find any polygon interior angle sum. Why? You ask? Why? Why do I subtract 2 from the number of sides and multiply by 180? Well, thank you for asking. Somebody did have that question, right? We don't care why? Oh, I care why. I care why. So what you do is you think about, I'm starting with a quadrilateral, 4-sided. If I draw all the diagonals I can, remember diagonals work with non-consecutive endpoints. So that's not a diagonal. This one is, that's it, right? from one point, that's the only diagonal I can draw. And I get two triangles. So if I have a four-sided figure, I get two triangles, right? What is the sum of this triangle's interior angles? And then, so what is the sum of these? That's also 180, right? I have two triangles. Each one has interior measures of 180, so it's going to be 2 times 180. That gives me a quadrilateral. What about a pentagon? So I'm going to do the same thing. You pick a vertex and say, where are all the diagonals I can draw? That's not a diagonal, but that's not a diagonal. So if you have a 5-sided figure, how many triangles do you get? 3. And then each of these triangles, how many degrees? 4. So if I want all of them, I just say 3 times 180. You see what's happening here? Hexagon, same kind of thing. Well, the two sides here don't count because they're consecutive, right? So the number of triangles you get is always going to be 2 less than the number of sides because I don't count these consecutive ones. Does that kind of make sense? So that's where my n minus 2 is coming from because I'm always going to be able to create n minus 2 triangles, and each triangle's interior angle sums add up to 180. So if you have a hexagon, you can get 4 triangles, so you multiply that times their triangle sum. A heptagon is 7-sided. You're going to get 5 triangles, so you do 5 times 180. Yes, sir?
With odd number drawings, would you always get the same amount of triangles no matter where you put the decimals?
What do you mean by that?
Like, see how a heptagon is like oddly shaped because it's an odd number of sides? No matter where you put the diagonals from one vertex, it will have the same amount of triangles.
No, a 7-gon and say like a nonagon, like here's 5. So that's also odd. So you're always going to be 2 less the number of triangles. It doesn't matter even or odd number of sides. And why is that? Because you create diagonals by connecting non-consecutive vertices. That's consecutive and that's consecutive. So 2 of them always get knocked out, but then you will be able to do the other ones. So that's why it's always 2 less, regardless of whether it's even or odd. That's a good question. Good question. So that's where that comes from. Now we have this corollary, which is the sum of the measures of the interior angles of a quadrilateral is 360. I could make kind of an infinite number of corollaries if I wanted to, couldn't I, for all the different polygons. We just tend to use this one a lot. So we're just going to remember that one. And if you can't remember it, use the formula. Alrighty. So examples, interior angle, find the measure of the sum of the interior angles of a convex pentagon. And remember that convex means that all these angles are not reflex angles, so this is a convex pentagon. I want to add up this one, this one, this one, this one, this one. So I use my formula, which is n minus 2 times 180. What's my n?
6 or 5.
5, it's a pentagon. 1, 2, 3, 4, 5. So 5 minus 2 times 180. I'm going to have my calculator print something out here. 3 times 180?
540.
540 degrees. So if you add up all these angles, you will get 540 degrees. Now here I've got a dodecagon. How many sides? What's n? 12. And if you're kind of like, what? I can count them. Now these get kind of complicated to count. I like to put a little marker from starting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's what a dodecagon looks like. I think I heard a comment. It looks a little like a circle.
Yeah.
Did you make that comment? What happens the more sides you get in a polygon? It gets more circular, right? You can almost think of a circle as a polygon with an infinite number of sides. You can almost think of that in that way. This reminds me, I have to put a plug for this book in. It's called Flatland. Written by Edwin Abbott. Has anybody read this book? It's an awesome book. If you have any kind of interest in math at all, it's a book about a two-dimensional world, and right, two-dimensional. And if you have it's made up of polygons and other geometric shapes, and the more sides you have, kind of the better or upper class you are, and the closer you get to being a circle, which they consider the perfect shape, the more perfect you are. It's kind of like a class society. It's an amazing book. I highly recommend it. Not only if you have an interest in math, but just interested in society, and it's fantastic. This is, adult level book. It's fantastic. So if you're looking for something to read, I recommend it. Anyway, back to this. I guess you're right, the death one. I'll look it up later. So anyway, how do I do this? So it's going to be 180 times n minus 2. So that's 180 times 12 minus 2. which is 180 times 10, 1800 degrees. You add up all those angles, you get 1800 degrees. That's a lot of degrees. So, like, what do you do with this then? Oh, we don't know yet. We're not there yet. Find the measure of an interior angle of a regular polygon with n sides. What am I doing here? Let's say I have hexagon. I don't know. I'm making something up. And it's regular. So what does that mean? Yeah, what does that mean? Equilateral and equiangular. So all the sides are congruent. All the angles are congruent. And I want to find what's one angle. Okay, interior angle. Well, what would be the sum of all of them? Well, what's the formula? Find the sum of all of the, you would add that up and get a number. You just do that? Yeah. Right? So, and now you're kind of going back to my general case. You find how much they all are inside. Now, each angle inside here, they are, let me think I want to go here. Each angle in a regular polygon is congruent, isn't it? Okay. So if I want to find the measure of one angle in here, how can I do that? Can I think of a formula that would work in all cases here for an n-sided polygon? Yep.
18 divided by n.
So this is basically the interiors divided by the number of angles that you have, right? Because all the angles are congruent. Think about what you do with a triangle, right? It's 180 divided by 3, each one is 60. So you find out what the whole thing is, and that's my formula for that. And then what do I divide by? N. It's the sum of the interior angles divided by the number of angles that you have, because all these angles are congruent. So let's do an example. What's the measure of an interior angle of a regular pentagon? So what's my n if I have a pentagon? Number of sides? 5. So I have to find how many, or what the sum is of all the angles, and then divide by the number of angles I have, which is 5. So do 180 times 3 over 5. We did 180 times 3 is 540, right?
Yeah.
What's 540 divided by 5? 108 degrees. So if you have a pentagon, that's regular. Now, does this work if I don't know it's regular? Can I use this just any old pentagon? Why not? Right, they have to be equiangular. So that's only in a regular pentagon. So you can use this formula if you know it's a regular figure. Make sense? Yeah, kind of. Okay. Moving along. This is for all those people who wrote I go too slow on my survey. Moving along today. Okay, polygon x, and then there are people who wrote I go too fast. I don't know, I can't believe. Polygon external angle theorem. The sum of the measure of the exterior angles. First of all, what's an exterior angle? Here I've got a pentagon. These are interiors, right? Here, 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 here. Now if you extend the line, this is an exterior. That's an exterior, 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 exterior. The sum of the exterior angles is 360 degrees. Always. No matter what kind of a polygon you have. What? Look at that big. That's what? So it doesn't matter how many sides you have. You are always going to add up to 360 on the outside. And it's kind of, I think, worth thinking about. So the sum of the insides, right, is n minus 2 times 180. We know that, right? Think of these linear pairs here. Now, the sum of all the linear pairs, if I were to add these all up, they're going to be 180 times n. Now, how come? What does a linear pair add up to? And how many of these linear pairs do I have? Well, in this case, I have 5 because it's a pentagon. If I had a hexagon, how many linear pairs would I have all the way around? 6. If it's an n-gon, how many would I have? Okay? So that's all adding up all the linear pairs. Now, if I take those linear pairs and I subtract out the interior angles, what am I left with? The exterior angles. Right? That's this. So that's saying if you start with the all the linear pairs and you subtract out the interiors, which is this sum, right? Let's see what we get. We get 180n minus, well, that's a 180n, negative, that's plus 360, right? Now, I'm just, distributing. That goes away, look at that. So it does not matter how many sides you have. Exterior angles will always add up to 360. Nice, easy one. So let's do a couple of examples here. We want to find the measure of the sum of these exterior angles of a convex 18-gon, meaning it has 18 sides. What's the measure of the sum of those exterior angles? What's the theorem again? Yeah? n minus n minus 2 times 180. What is that always going to be? So what is the sum of the measure of the exterior angles of a convex 18-gon? What's the sum of the measures of the exterior angles of a 100-gon? 360. What's the sum of the exterior angles of a triangle? 360. So this is like the easy one. So make sure, when you answer these questions, make sure you know what you're looking for. Sum of exterior angles, the answer is 360. Now, if you're getting a problem like this, how would you go about solving this? Yeah?
All of those equals 360.
Yeah, we're basically going to add all this stuff up, and it has to be 360. So let me see if we can do this. We got 4x plus 6x, 10x, 15x, 20x, 22x, 25x. Make sure I'm doing this right, because you have that in with this kind of thing. That's a 5, and a 4 is 9, and 2 is 11. 14 minus 4, I want to say 10. What's it going to equal? 360. If I subtract 10, 350. What do I get here? If I did this right? 14. To 14? Okay. So this is where we kind of use these formulas. Equals 360 on the exteriors. Questions so far? I'm going fast. Okay. Exterior angle of a regular polygon. So we looked at the interior angle of a regular polygon. What about exterior? What's the sum of the measures of the exterior angles? Each angle in a regular polygon is congruent, or the same measure. So how would I find one exterior angle in a regular n-gon? I want to find one. Yeah. 360 divided by the number of sides. Think about a triangle. So if it's a regular triangle, that means it's an equilateral triangle. You just see 360 over 3. You get 120, right? Isn't that correct for an isosceles triangle? Interior is 60, and they add up to 180. So let's see. In a regular convex polygon, this is a useful thing to kind of remember. An interior angle is 180 minus the measure of an exterior. So, and again, that's just like you have a linear pair. So here's your interior, here's your exterior. So if you know the exterior, you can easily find the interior by doing 360 minus this value. So it's another way to find an interior angle in a polygon is to find what this is, and then subtract that. What's the measure of an exterior angle of a regular hexagon? So when I do these, I kind of underline, so I know what I'm looking for here. Exterior angle, regular hexagon. What's n? 6. How do I do this? What is exterior angles? What do they all add up to? And then how many angles do I have? 6, right? Hexagon? So 60 degrees? That would be the measure of an exterior angle. For some of the smaller ones, if it helps to kind of draw the picture, this is what I just found. 60 degrees. This one also, 60 degrees. Regular. Can't do this if I don't know it's regular. What is the measure of an interior angle of a regular hexagon? Yeah? 120. How'd you get that? Yeah, if this one's 60 and this is a linear pair, 120. It's an easy way to get to that. The other way to do it would say, well, it's going to be 180, 6 minus 2 over 6, right? Isn't that how you find an interior angle? and it's work. I don't have to do that. I can just find the exterior angle and do 180 minus that. So another way to get there. Alrighty. Not so fast. Okay, examples. Find the sum of the measures of an interior angle of a convex octagon. Octagon. Oh, that's too hard for me to draw it. Yeah. What's N?
8.
How do you find the sum of the measures of an interior, the interior angles? What's that formula? Yeah?
N minus 2 and parentheses multiplied by 180.
Okay, so N is 8. So 6 times 180. Somebody type that in for me. 1080 degrees. Done. The sum of the measures of an interior angle of a convex polygon is 900. Classify the polygon by the number of sides. So the sum of the interior angles, right? Interior angles is 900. How do I find the sum of the interior angles again? Yeah? Yeah, he's kind of taking this apart. He's saying, well, that's the formula, right? So you'll divide by 180. And then I'm going to add 2, and I should get my N. And so this should work for kind of any situation like this. If you know what the sum is, put that here, divide by 180, and add 2. What do we get here if we do that? N equals 7, so this is a octagon. Yeah, so we're just working with these formulas, going back and forth with them. Questions so far? I know I'm going at a good clip here, so stop me if you have a question. All right, more examples here. How would you go about finding X? How would I do it?
Add all of them.
Yeah, go ahead, Sarah.
Add all of them equals
360. So now you have to think about what these all add up to. We're remembering that corollary, so for this it's going to be 360. So X plus all these things has to equal 360, which, I don't know, tell me what you get. Anybody get something else?
X equals 72.
I got X equals 72. Did you add this up? So X plus 280, is that what you were doing, Brenda?
Yeah.
Yeah, that's fine. So I'm letting you kind of solve that simple equation. How would I do this guy here? I want to find the value of X, for example, D. Yeah, Deja, what would you do here?
You would add up all the angles,
Set it to 360. Exterior angles always add up to 360. So 2x plus x plus 89 plus 67 has to equal 360. All the exterior angles, they always do. Anybody find x yet? I'm looking for what's x? Mr. Alex. 68? Is that what we're getting? Leave this for an exercise for you to solve that equation. So 68 degrees for this one, and whatever 2 times 68 is for that. We want those measures. And then we got the measure of an interior angle of a regular polygon is 140 degrees. Cool. So what's going on here? I've got some kind of polygon, and I don't know how many sides here, but the measure of an interior angle of a regular polygon, right? So all the sides and all the angles are congruent. It's 140. How many sides? Oh, this one's a little bit more thinking involved. How do you do that? There are, there's a couple ways to think about it. Let's say I knew how many sides, and I know it's regular. How do you get an individual angle? Do you know how you do that? Don't you say, well, what do they all add up to, right? That would be the sum of all of them. And you divide by the number of angles you have, right? That gives you one of them, and one of them is 140. So I can go ahead and try and solve this, right? Oh. So multiply both sides by n. You know how you do this?
Yeah.
And then, let's see, I guess I should maybe distribute it, I don't know. So let's see, 180n minus 360 is 140n. Then I gotta subtract 140 and add 360. I hope I'm doing this right. I'm doing it a little quickly here. Is that, so what's n? 9, is that right? I hope it's right. Oh, I'm stuck in this thing. Now, that's a lot of work. There's another way to actually think about this. How about this? If this is 140, what's the exterior angle?
40.
Right, it has to add up to 180. How do you find one exterior angle in a regular polygon? What do they all add up to in the exterior? And since it's regular, they all measure the same thing, right? So you divide by the number of angles, and what should I get? 40. Remember how you solve this? This is, I can do a little swapsies here because the product of the means equals the product of the extremes. So I could just do 360 over 40 would get. So questions like this where they give you an interior angle of a regular polygon, I think it's a little bit easier to find your exterior. 360 divided by that measure will give you the number of sides. So this is a nonagon. We're following it all because I am going fast. You're with me? Who's with me?
That's the second part.
We got the second part. The second part's easy, right? It's the algebra's easier, less likely to make a mistake. Alrighty, so we're up to the U-tries already. So, my friends, it's up to you. I'll put the answers up. Give them a try. While you're working, my suggestion is what am I finding? Sum of interior angles. For now, look at your notes. Make sure you're using the right formula. That's this one. Right? The sum of the measures of the interior angles is a number. So you have to find number of sides. You're going to solve for n. You got to find a number of sides. Yeah, I think you can do this. So I'm going to let you work on that a bit, and then we'll regroup, hopefully. This is the answer to the next page, so that you can kind of see what you should be getting. If you finish with the first one, that's yeah, this will all be posted, so you can check your work.